Alright, so we're going to review looking at chapters 4 and 5 of our textbook, which is really our trigonometric identities. So the first one, we're just asked to get our Pythagorean identities, and it comes from the Pythagorean theorem. So if I was to take the picture that we have on the right and figure out sine of theta, which is opposite over hypotenuse, in this case y over 1, and cosine of theta, which is adjacent over hypotenuse, which is x over 1, I get x and y. If I use the Pythagorean theorem, I know x squared plus y squared equals 1 squared, and if I substitute in sine of theta and cosine theta for y and x respectively, I get my Pythagorean identity. And then we manipulate that two different ways to get variations on it. So if I divide everything by sine squared of theta, I get cosecant squared theta equals 1 plus cotangent. And then if I divide everything by cosine squared theta, I get my third variation of the Pythagorean identity or Pythagorean property. So again, an identity is something that's always true, and so these are values or pieces where if I know one piece of it, I can find the other piece, and it's useful for what we're going to do next, which is verifying or proving identities. So if I'm asked to prove an identity, I have a left-hand side and a right-hand side, and somehow I want to turn one of those sides into the other. And it's always helpful to start with the more complicated side. It might be counterintuitive, but it allows you to perform some operations. So if we take the left-hand side, and I get a common denominator, and bring everything together. So I first off change my secant over sine theta into cosine theta. Sine theta is my denominator. I need a cosine theta sine theta for my common denominator, which means that the sine theta over cosine theta needs another sine theta. That all turns into sine squared theta minus 1 over cosine theta sine theta. Sine squared cosine theta over 1 is negative cosine squared over cosine theta sine theta, and that comes from our Pythagorean identity that we did at the top, the one that is up here. So we're allowed to use that and plug it in to our value down there. So that gives us that piece, and now we have to simplify and see what happens. So if I simplify, I get negative cosine over sine, which is negative cotangent, and my right-hand side. The other one looks scary, but if I bring everything together with a common denominator, and replace my values with cosecant as 1 over sine, and distribute that through, a lot of things drop out, and I get a simple numerator of 2. The bottom is cotangent squared, and when I have a reciprocal of cotangent, or cotangent on the bottom, that is tangent, so I get 2 tangent squared, which is my right-hand side. So again, I want to take one of the sides, usually the more complicated, and turn it into the other side. We also have what are called even and odd properties for functions, and it comes from, if we were to look at general polynomials and look at the degree, so the highest exponent, even and odd also have this property. So an odd function is defined as f of the opposite of x is the opposite of the function, so the value. That works out to work for sine, tangent, and cotangent, as well as cosecant. Even is where they're the same. So if I put in the opposite angle, I get the same function value. That works for cosine and for secant. So that's kind of an aside. They're properties that we can use for verifying and proving things, but they don't pop up as much as some of the Pythagorean identities. All right. So more often than not, we're asked to solve something where we have to use an identity to get us there. So we take our value of sine of 2x. Alright, so we use our identities, or sine of our double angle identity to expand sine of 2x. And so what we're going to have to do is when we have something set equal to 0, we use what's called the zero products theorem, which basically if things multiply and equal 0, then each of those pieces equals 0. And so I factor out a cosine, now I just have multiplication. So if it's going to equal 0, that means either cosine of x is 0 or 2 sine of x minus 1 equals 0. Well, I evaluate this for cosine of x equals 0. Those are angles of pi over 2 plus pi n, so it's the top and bottom of my unit circle. And then I have to do a little bit more to get this by itself, but I add 1 and divide by 2, and I get sine of x is a half. And that happens at x equals pi over 6 plus 2 pi n, or 5 pi over 6 plus 2 pi n. So that's my general solution. For that on another interval, I would set n equal to 0 and get my values there. I would plug in values of n, and get all the ones that are between 0 and 2 pi. Alright, for the next one, I have either to bring it all to one side or get it all in terms of sine or cosine. So if I bring it all to one side and factor out a 3, and that put the 6 on the other side and divide by 3, I get sine squared x plus cosine squared x equals 2. Well, that contradicts our Pythagorean identity because we know it should be 1. So what this means is that we have no solution. There's nothing, as the empty set. There's nothing that'll work that'll allow us to make that equation true. So it's not possible. We're looking for, if we were to graph it, we'd have points of intersection that aren't happening, that they don't meet, the lines don't cross. All right, in terms of parametric equations, to do it, first is to get a table. So if I make an x, t, and y table, and I plug in my values, so I'm going from -3 to 2 just because it told me, if I look in this interval here, right, that tells me what I have to go from the minimum to the maximum t. Now, it doesn't tell me what I have to count by. So I just decided to count by 1s. I could have counted by something different. That's called my t-step. And that might actually change what the graph looks like depending on what t-step I pick. But for this one, it's not as big a deal. If I'm looking at a circle or an ellipse, and it is more of an issue. But anyway, all I do is I plug in -3 for t and to x and y, and I get values for x and y. So if I do that for x, I get those numbers. If I do that for y, I get those numbers. And now what I'm going to graph is those ordered pairs. So the x and y as I normally would. I plot those, and I have those points. Now, if I was to change my t-step, maybe count by a half instead of 1, I would get points in between those. And my true function is for t can be any number in there, so I would connect those lines to those dots to get the full picture in terms of what I have going on. Now, if I really wanted to look at this as we normally would, I need to be able to probably put it in Cartesian equation. But before we do that, let's look at B, where basically I'm putting in a value for x and y and solving for t. So if I put in -12 for x, I solve for t and get 6, and I can just check it for y. Does that work for y being 24? It does check, so that's pretty simple. But let's say I want to get rid of the parameter and I put it in Cartesian form. It's called eliminating the parameter. What I'm going to do is solve for t in terms of x and then substitute. So I plug that into the equation with y. So now I have something with just x and y in it. I do some simplification and I get this shape, which is going to be a parabola. So I can see that I have that parabolic shape that's happened within my graph, where I just have half of it because of the restriction on t.